ทดสอบได้เวลาฮัลโหลทดสอบ Okay, so good afternoon. Start. Okay, so we are discussing review of constraint analysis very quickly, 1 hour. So let me first give you a quick motivation for study constraint analysis. So the constraint analysis studies dynamics of constraint systems and what are constraint systems. Basically, for example, gauge system which has gauge symmetry, or gravitational system which has diffeomorphism symmetry, or what we also call general covariance. Or you may want to construct some system which has got a violation of gauge symmetry. For example, you might produce a mass into theory, Procard theory, or you may want to produce mass to a theory to get gravity, and then you may want to check if the dynamics is okay. So this is in order to study the dynamics. So actually, in this morning we have welcomed you with some nice picture of space-time that is space-time continuum, space and time on equal footing. But in order to study dynamics, we will have to do something less beautiful. So we have to make time at higher priority, because when we talk about the dynamics, we talk about what changed in time. So let's just start with the theory. So the study of constraint analysis, there is one popular method. It's the algorithm by Dirac and Bergman, which is still used. Okay, so let's just first start from a system which has got generalized coding, which we will label as Q or I. I runs from 1 to n, so there are going to be Q coordinates. And let's suppose that we are considering isolated system. So basically, there is no external source system. So our Lagrangian would be in terms of Q and Q dot. There is no explicit time dependent. That's only depending on Q and Q dot. So depending on time through only Q dot. So we have got Euler-Lagrange equation, which I've seen so if you want to study the dynamics of the Lagrange equation, and you might have also called them equations, but strictly speaking, not all the equations tell you about the mode. Some equations would actually constraints. I will more explicit what it really means. So if you use the chain rule on the derivative with some rearrangement, this is what you could have. So this is the only place where you have got the accelerations. The other expressions only contains Q and Q dot. Okay, and we call this as a Hessian. And if we consider the case where the determinant of Hessian is non-zero, which is, for example, what you have seen in undergraduate physics. I mean, in those cases, you are often be able to, you would always be able to have the inverse multiplied by this inverse, and then you can have all the equation which you allow you to, in principle, integrate the Q. I mean, to get Q as a function of two variables, Q as a function of 2n constants, or up to 2n. Q would depends on 2n arbitrary constants in those cases. But what we are interested in are not that case, which was quite relatively simple. What we are interested in is the case where determinant of the Hessian is 0. In this case, you are not be able to find an inverse. The inverse doesn't exist, so you cannot use the same kind of analysis. So it would turn out that if you rearrange the equations, you will encounter some equations which only contains Q and Q dot. So you will have got some equation contains Q and Q dot at every time. Okay. So I forgot to mention that actually in the case where the Hessian determinant of Hessian is non-zero, you will be able to write Q in terms of 2n variables, and we take the 2n variables to be initial position and initial velocity. But in the case where Hessian determinant is 0, it would mean that Q and Q dot are corresponding to each other. I mean, depending on each other by some of the equations, and then which would mean that at times t equal to 0 itself, these variables, these initial data are actually dependent. Okay, so basically you don't have all the 2n independent variables. Okay, so or in other words, the number of independent variables are less than 2n. And this is the example of the, or not an example. This is the indication of the constraint system. So having got the Lagrangian, we would now work out the conjugate momentum. So P is a function of Q and Q dot. And for the constraint system, what would happen is that you are not be able to write Q dot as a function of Q and P. I mean, for the unconstrained system, you were allowed to do this. So, but constraint system, you are not allowed to. And or if you look at the Hessian matrix, it will have got has K0 modes. Which means that eigenvectors corresponding to 0 eigenvalues. And in practice, you can rearrange this equation itself to get equations that only depends on Q and P. So rearrange this. So some of the equations would contain second order derivative in time. Some equations, no, sorry. Some equations will contain all Q and all P, Q, and Q dot. Some equations will contain just only a function of Q and P. And we call this as primary constraints. And these primary constraints, the number of primary constraints is the same as the number of zero modes of the Hessian. So what it does is that it defines a surface in the phase space. So if you have got a phase space, so this is the space of Q and P. Of course, you can draw a motion on the phase space, but the thing is that the trajectory of the system would only be on a spatial surface, and this surface is the constraint surface. And this is what defined by the primary constraints. Okay, as you can see that the trajectory has to be like Q as a function of T, P as a function of T, but they have to be related through those equations. So which means that the trajectory is on the constant surface. Next, let's just try to proceed by consider the Legendre transformation to define the standard Hamiltonian, which we call canonical Hamiltonian. So which is just P Q dot minus Lagrangian. And if you consider taking the D, then in the end, after some calculations, this is what you get. So as you can see that the canonical Hamiltonian only depends on P and Q from here, because the DH is in terms of only dP and dQ, not of Q dot. Okay, so this is the canonical Hamiltonian is a function on the phase space. Now, on the other hand, we may say that since Hc is a function of Q and P, we take the derivative by using just the chain rule. And then we compare the two equations, the two expressions of the Hc. This is what we get. Okay, we are particularly interested in what happens on the constraint surface because this is the place where the dynamics occurs. On there, it turns out that the set of all the dq's and dp's this set is actually not independent on the constraint surface. And it means that we cannot just simply say that, oh, this is equal to 0, this is equal to 0. We would only be able to do that in the case where this set is independent. But instead, when it is not independent, so actually we have to see what is about the constraint surface. So we have got the gradient, which is perpendicular to the constraint surface. So any vector that is on the constraint surface would would be perpendicular to this, which means that we can say that, oh, this guy is equal to 0. So this is just the equation that says that the gradient of the primary constraints q's all the vectors on the surface. And this translates to the equation after using the chain rule. Okay, and only here that we can compare with this equation. Okay, so for example, we compare this with this, and I forgot to tell you that you can have a UI to be any functions on the phase space. Okay, after you compare this, what you get is so basically what it says here is that the Hamilton equation is not just given. Is not by the canonical Hamiltonian, but you will have to introduce extra term, which also depends on the some arbitrary function u, which which we can recognize as Lagrange multiplier. Okay, actually, it is more convenient to define another Hamiltonian, which is going to be called the total Hamiltonian.
Can I ask a question?
Yes.
So on the constraint surface, phi I is always 0.
Yes. Yes.
So considering d phi I means moving outside constraint.
Yes. Yes. So this is just the gradient, the gradient of the of the constraint surface.
And ui d phi I is
like
You make linear combination basically of these gradients.
combination of that
Yes.
gradient.
Yes, and the linear combination would still be perpendicular to vectors that are on the surface.
The UI is on the surface.
UI is just some function. You can imagine that you have got many phi I. I mean, this one surface is defined by many phi I, and then you consider many gradients. You take linear combination of the gradients. The UIs are the coefficients of these.
Is it related to the like surface? So d phi I is perpendicular to the surface.
Yes, the phi I is perpendicular
So
to the surface.
the UI d phi I is kind of like and it's roughly the dot product between UI and phi.
Not dot product, but more like linear combination. So you okay? So if you write in terms of the vector, you would have got like you let's say something like this. I'm not sure if it was up to k or yeah. Let's suppose that it's up to k. So it's something like this. You make a linear combination of the of these vectors, and the u's are the coefficients, and actually is not just constant. These are functions of space time. Sorry, of the phase space.
The linear combination is 0 because each
Yes, because each is perpendicular to the vectors on the constraint surface.
cube.
Okay, so let's just back to the total Hamiltonian. So as we can already see from the Hamilton's equation that we should define the total Hamiltonian as the canonical Hamiltonian plus an extra term. So basically, you may recognize this as introducing Lagrange multipliers. So these U's are just Lagrange multipliers. That would enforce phi I equals to 0. Okay, but let's just now check if we can write the Hamilton's equations in that terms by using the total Hamiltonian. So let's consider okay, and similarly for the P. Okay, sorry, I'm not going to write down in details, but what we can see is that it's not exactly the same as there is an extra term here. But this term is not going to cause a problem for us because we are only going to consider the constraint surface. So on the constraint surface, phi I itself is 0. So we can ignore this term itself. Okay. And although phi I itself is 0, you don't say that the derivative of phi I with something is 0. This is in general not 0 on the constraint surface. So all you can do is saying that this term is 0. And then after some calculation, you can, no, not some calculation, just after some substitutions, you can see that the Hamilton's equation is just this on constraint surface. Okay, and I don't want to write every time that or say every time that the equality is just only on the constant surface or the equality is throughout the phase space. So there is a notation which distinguish between these. And for this, let us consider two phase space functions. QP and we say that f equals to g. This means that equal everywhere. On phase space. And this is called a strong equality. And we also have another thing, which is weak equality. So we use the approximation sign, which means that it equals only on, I can say equal everywhere still, but on constraint surface. Okay, so this notation means that I copy from above. So this is equal everywhere on constraint surface or the weak equality. Okay, so with this notation, I would as well use the weak equality here. And I don't even need to say that is on just only on the constraint surface. So just say this is already enough that the Hamilton's equations holds on the constraint surface. This, I mean, in this form. Now let us consider the consistency requirement. Let me reuse this picture. So consistency requirement is just simply to say that the system trajectory should really be on the constraint surface. And this is translated to the requirement that phi dot I is to be equal to 0 everywhere on the constraint surface. Okay, so what you do is after you get the primary constraint, what you do is you take derivative with respect to time and then demand that it is equal to 0 on the constraint surface. And in the calculation, you would also want to use this identity that or the relation that actually the time derivative is given by the Poisson bracket with the total Hamiltonian. Okay, I hope I don't need to write down what the Poisson bracket is, right? Or does anyone want me to know? Okay, good. Now, it would turn out that this is not automatically satisfied in general. Okay, so if we do some calculation, I mean, basically substitute the HT into here. So what we get is that okay, what is important here? I mean, one thing is that this weak equality contains this U here. So you may want to, I mean, in practice, you may want to rearrange all these equations. I mean, one equation for one primary constraint. You rearrange these equations, and what would happen is that you might get some trivial solution. Some trivial equations, but there are going to be some equations which allow you to so you will get some non-trivial. So ignore the trivial conditions because we are physicists. We don't want something trivial. So non-trivial conditions are going to be conditions on Lagrange multipliers. Or it would tell the existence of extra constraints, which let's just call secondary constraint. In particular, this condition is important. Okay, let's just call these secondary constraints as phi I prime, and we redefine the constraint surface. So originally, the constraint surface only is only described by primary constraint, but it turns out that actually we should also combine the secondary constraints also. So the new constraint the actual or more accurate constraint surface would be described by setting primary constraints to be 0 and the secondary constraints to be 0. And after you have got the secondary constraints, you would want to check the consistency again. I mean, the consistency for the primary constraints is already satisfied. You have already worked out here. But for the secondary constraints, you have to also work out. And then you will get some equations like this. But in that case of secondary constraints, it would be something like instead of I, you have got the index I prime. For example, if you label the secondary constants by using index I prime, you work out this equation, you look for non-trivial conditions and to see if there is an existence of extra constraints. If you get existence of extra constraints, you keep checking the consistency, which would be that the extra constraints taking time derivative would be equal to 0 on the constraint surface, and then repeat the process until you don't you no longer get this existence of new extra constraint, and you end the process, which would mean that you have discovered all of the constraints in the system. And once you have got all the constraints, you collect the constraints. So let's say I denote the collection of all the constraints in this way. Okay, and then we are going to classify. Okay, so forget about all the primary constraints, secondary constraints, forget all about the name. Everyone is in here. Okay, we will call them with a new name. So basically, let's just talk about, define what first class function is. So first class function means that it's weekly Poisson commute with every constraint. If it is a second class, if a function is not a first class function, we say that it is a second class function. And we want to classify the constraints themselves to be either first class constraints or second class constraints. Okay, maybe I'm skipping the classifications, but the idea is that you are going to classify. You may want to do some linear combinations of the constraints. Okay, there is a matrix which actually allows you to count the number of the constraints. So I have to say this anyway. So you look for the number of zero modes of this matrix. So the number of zero modes is the same as the number of first class constraints. So suppose that you have found the K1 zero modes, which means that you are going to get, if you have got K1 zero modes, you are going to get K1 first class constraints. Okay, you may want to make some linear combinations to get K1 first class constraints, and the rest are the second class constraints. Okay, and okay, so let's say first class constraints. For example, I label it by phi A and second class constraints. I label it by chi alpha. And if I consider this, the matrix formed by just the Poisson brackets of the second class constraints, this should be invertible. Or in other words, there is no zero mode, as the zero mode corresponds to the first class constraints. Now, suppose that you have finished classifying into class, basically. So you can now count the number of degrees of freedom. So this is given by 2n minus 2 times the number of first class constraints minus K2, which is number of second class constraints, and divided by 2. So 2n is the total number of first space variables, okay, and K1 is the number of first class constraints, K2 is the number of second class constraints, and you might be worried that this is going to not be integer in some case, but it would usually happen that K2 is an even number. Okay, that is a way to prove, but let me not do it. Okay, so here is pretty much what we have here. So let's us now consider some examples which hopefully would make it easier to understand the process. Okay, you have already seen what the Lagrangian density for Maxwell's theory was, and actually F mu nu is, can be should be given in terms of the A, and then we would vary this with respect to A, basically. Okay, so the conjugate momentum is that we take derivative with respect to the A dot. And when mu is equal to 0, you see that we get pi 0 equal to 0. Which means that you have already got a primary constraint. Which is pi 0 is equals to 0. And you may want to, if you want, you may check with the Hessian and look for the number of 0 modes, and you will see that there is just only one 0 mode here. So which means that we have only one primary constraint. And you can work out the canonical Hamiltonian density. So after some calculations, this is what you get. And the total Hamiltonian density is given by Hc plus U times pi 0. But when you want to compute the time evolution, you will still have to make the Poisson bracket with the total Hamiltonian, not the Hamiltonian density. Total means that you integrate the density with the volume. Okay, so maybe I need to skip the details here. That in the end, if you compute the primary constraint, the consistency of the primary constraint, you would get that, okay, just taking the derivative. This, you can compute this from this Poisson bracket relation. Okay, and requiring that pi dot 0 equals to 0 means that partial I pi I should be equals to 0. So this is a secondary constraint. So let me call this as phi 1 and call this as phi 2. Okay, we have a take derivative of phi 1 with respect to time, and then we consistency requirements gives us that the a secondary constraint, and we can work out the phi 2 dot goes to 0. Then it would give no further constraint. You may want to work it out as an exercise in the tutorial. And if you want to classify, you see immediately that, phi 1 is pi 0, not pi 0 dot. you see immediately that this is just only depends on conjugate momentum, and phi 2 only depends on conjugate momentum. So immediately that the Poisson bracket between them is 0. So which means that both phi 1 and phi 2 are first class constraints. Okay, and if you count the number of first space variables, they are going to be 8. And you have got two first class constraints. And then substitute into the formula, you get two degrees of freedom. Okay, which corresponds to two photon polarizations. You may as well end it here for the analysis of Maxwell's theory, or you may want to do more. So when you have got the first class constraints, as Dr. Pongwit has mentioned that, I still not to that. Okay, again, after you have got the first class constraint, first class constraints would generate the gauge transformation, or each first class constraints corresponds to gauge symmetry, and gauge symmetry means redundancy. And you may want, so which means that when you have got first class constraints, what you want to do is you may want to fix the redundancy, or get rid of the redundancy by doing the gauge fixing. And we know from theory that in Maxwell's theory, if you use the Coulomb gauge, then we can completely fix the gauge. And to do this in constraint analysis, what we do is that we introduce extra constraints as gauge fixing condition. And the extra constraints that we introduce are okay, which just means that we demand that A0 equals to 0, and then the standard Coulomb gauge condition. And what you want to do is, since these are also constraints, you have to look for the chi dot 1 equals to 0 and chi dot 2 equals to 0, see if it introduce extra constraints. And you will see that there is no extra constraint, which I believe this is one of the problem for the tutorial. And alternatively, you may want to start from just the Coulomb condition. And then after you demand the consistency, you will get the chi 1 for free. And this is also a question from in the tutorial. Okay, and in any case, it means that you have got two extra constraints, which are chi 1 and chi 2. When you do the classifications, it turns out that there are only there is no longer first class constraints, but we now have got 4 second class constraints, because the original first class constraints now becomes the second class constraints. Okay, and you may want to count the number of degrees of freedom and see that it is still 2. Now, second class constraints. Okay, now if your theory, okay, you may as well end here. Or if you want to go further, if your theory has got just only second class constraints, what you would do is you want to solve these second class constraints. So you look at these as equations for phase space functions. You solve these equations to eliminate some of the phase space variables, and then you end up with a smaller phase space with smaller number of phase space variables and with no more constraints. And in the Maxwell theory, what you will end up with is that your reduced phase space would contain so just only you kill the zeros components, and as for the spatial path, you only have the transverse mode, okay, which would agree with what you would expect, that the polarization is in the transverse mode. And again, you may want to count the number of degrees of freedom, and then here you have got 2 transverse, here is 2 transverse, 2 plus 2 is 4, you divide it by 2, you get 2. Okay, now we move on to the gravity theory, in particular Einstein gravity theory, and I might not have much time to say this, but what's very important is that, as I have mentioned at the beginning, is that you have got a nice continuum of space-time. Well, I'm not sure if this picture really represents it, but what you would do is that, okay, if you don't consider the dynamics as we have done in this lecture, for example, then you would look at the space-time continuum as some nice thing that time and space are on equal footing. But if you want to consider the dynamics, you have to make the slices. You slice the time. You slice the space-time into many slices, or you may think of a bread, and then you slice off your bread, and then maybe consider one of the slice, and each slice is the constant time hypersurface. On each hypersurface there is a, or on each slice, we specify the value of time coordinates is fixed, okay, and as a result of wanting to consider the dynamics instead of which means that the covariance descriptions of the metric is not going to be useful for the study of dynamics. The dynamics should be dependent, in order to describe the dynamics, we should write the metric in terms of quantities that are related to the hypersurface. And so one quantity is so if you take the gradient here, it is normally not normalized, so you would introduce the normalization, which is n, and n is called the lapse function. And also, if you consider the time evolution of a certain point, so you would draw a curve, and in general, in the curve space-time, the vector that tangent to this trajectory, the time that the point evolved, and the gradient, they are not going to be in the same direction, and the mismatch of the direction is described by the shift vector. And you also need the metric on the hypersurface. And when you count the number of independent variables, is in total 10 variables. Okay, and if you work out, you can actually work out to see that the metric is separate in this way. Sorry. Okay, plus nj/dt. Okay, so this is called the ADM decomposition of the space-time metric. Okay, and basically, when we consider the Hamiltonian should be, depends on these variables as well as their conjugate momenta. Okay, and let's denote that the conjugate momenta for n is, let's say, pi 0, and for ni is pi I, and for gamma ij is zeta ij. You can write the Lagrangian in terms of these generalized coordinates. And then you will see that there is no time derivative on n and no time derivative on ni, which means that pi 0 equals to 0 and pi I equals to 0 are primary constraints. Okay, and then let me just write down the final result, that in the end your canonical Hamiltonian density is in this form. Where H0 and Hk do not depend on n and nk. And then from the consistency requirement, for the primary constraints, you would see that the H0 itself and Hk itself are also constraints. And this is called the Hamiltonian density. Sorry. Hamiltonian constraints. And momentum constraints. And then you work out to see if there are further constraints, and then you will see that there is no more further constraints, and then you would work out the classifications, and it would turn out that all the constraints that we have found here are first class constraints. So there are in total 8 constraints. So 8 first class constraints, 0 second class, and the number of phase space variables are 20. So 20 minus 2 times 8 divided by 2. So this in the end gives you 2, which is which agrees with the 2 polarization modes. I mean the plus mode and the cross mode of the gravity. Okay, and this is all that I have to say. Any questions?
Any questions?
Yes, my.
I want a little bit more clarifications, like why do we need to distinguish between the first class constraint and second class constraint? Why do we need to separately consider that?
Yeah. So good question. What I see the usefulness of first class constraints is that when you have got first class constraints, it means that your theory has got gauge symmetry. And actually, when you work out your first class constraints, you can even use the first class constraints to generate the gauge transformation. You can see from your calculation what the gauge transformation looks like by using the first class constraint. So you don't need to guess what is the gauge transformation of your theory. I mean, for example, some other approach would be that you start from the Lagrangian. You guess that your theory has got you guess that your theory has got this and this gauge transformation, but you wouldn't be sure that whether these are all the gauge transformations of the system. If you want to do it systematically, you would follow these steps, and then after you have got first class constraints, you use first class constraints to generate gauge transformations. And okay, as for second class constraints, I'm not sure, but I think the one purpose is that after you make the gauge fixing and then you have got just only the second class constraints, you queue all the second class constraints along with some components of your phase space. Okay, and then you end up with what's really contribute to the motion. And if you want to just count the number of degrees of freedom, I mean, in some case, in some theory, you would see that, if you have got too many degrees of freedom, some degree of freedom would be ghost degrees of freedom. So you want to make sure that you don't have too many degrees of freedom. So having got the number of first class and second class constraints allows you to compute the degrees of freedom, and sometimes that's all you need.
Any question? That is good question, and then that is one of the main point that we can go further on modify gravity. In case when you try to modify gravity, you have to add something, right? So that if you add something or you can make the Lagrangians more general, usually you get more degree of freedom. So that in that case, it may be code degree of freedom and then make a theory unstable. So that you need to know how to kill it. If you want how they emerge in the phase space, something like this, you can find the way to kill it, to kill that degree of freedom. That is quite important. I think maybe Professor Pichet to tell you how to get it off somehow. Okay. Any question more or any more support?
That's all I know. Anything else?
Anyone? Any more questions? If no more question, please thank speaker again, and then we have breaks outside here. And if some of you don't have what I call password for Wi-Fi, NU Wi-Fi, you can take here. ไม่แน่ใจเทศI think this is a time. So before I give a lecture, I have a good news and a bad news to tell you. What you want to get first? Bad news. Okay. For the bad news, Professor Pichet can get inside with us because they have war in Russia, so that he cannot get in flight in time. Actually, flight cancel, so that he will give a lecture online. Okay, that is bad news. For the good news, you all are forced to give a talk, just fat talk. I mean, all of you need to give a talk in 5 minutes, and then I will ask you to give topics soon. Maybe I will let you get in Google Form, and then you can give us a topic of your talk. The talk is a flat talk, just 5 minutes, so that the main objective for this talk is just give you to present yourself or introduce yourself to your friends, and then you can introduce your work also in case somebody want to talk with you, and then somebody maybe work nearby of your topic so that you can discuss later. Okay. Now, so any questions about this? If no more questions about this, I will go to my lecture. For my lecture, this is not my lecture, right? This is a topic, general relativity, takes in the morning. It's just basics, basic theory you need to know first, and then Ajahn Labum give you review on this, and then also this is just basic ingredient you need to know, a basic field theory. Ajahn Pam also give you, and then the constraint system, Ajahn Pichet give you, is like a tool to move further when you try to modify something, as I told you before. So my topic, cosmology, cosmo. The cosmology is just, it's not a basic ingredient, but it's still you need to know, because the topic of school is modified gravity, right? So that you may ask why you need to modify gravity. So that one of the reasons come from cosmology, because we know that the universe expand with acceleration, so that we cannot use general relativity, the basic general relativity with normal matter to describe that event. So that you need to modify gravity, or need to put exotic matter to the theory, so that Cosmo is just a basic thing you need to know before go to the full lecture, because when you go to the full lecture, the lecturer will tell you that if you modify like this, how can you how the result match with the observation, mostly in cosmology observations, cosmological observation. So that I just give you a basic review. Because this topic quite very large, we can take a course for these topics. So that here also like a GR and field theory, just review. Okay, let's start. Or if someone if you have a question, you can raise your hand and ask immediately. Okay, cosmology. The basics idea of cosmology. Once you know about GR, you need to use GR to describe the dynamics of the universe. For example, so that this is the main idea of cosmology. You try to explain how the universe evolved, what is the ingredients of the universe, so that you need to use GR because you may imagine that the universe has matter, and then the matter make the universe have dynamics. Okay, and then as you know from in the morning class, in GR you have Einstein field equation. So that you need to solve these equations for the universe. And this is a couple nonlinear differential equation, 10 equations, so that it's not possible to solve by hand, or it's still difficult when you try to use computer to solve it. And you need some symmetry to make it easier to solve. What is the symmetry you need? What is the symmetry you have in cosmology? Okay. Someone can tell me? It's come from what we call it just cosmological principle, right? So that what is a cosmological principle? It's a kind of it's not in the first. It's not a kind of principle. It's just some kind of philosophy thing, because in the first time we try to explain the dynamics of the universe, and then we just convince ourselves that we have to use the theory we have to every place in the universe, so that universe should be in the same, I mean, not spatial point in the universe, so that we can apply our theory to every place in the universe. So that this is a kind of thing that we have just isotropy and homogeneous and isotropy. I mean, the universe need to be homogeneous and isotropy. What does it mean? It means that for isotropy, when you look at any direction, it should look the same. In this case, it's up to cosmological scale. I mean, if you go to the cosmological scale, it's scale like the galaxy is just the sand in the beach, so that is very smooth. In this case, when you look it in any direction, you will get the same. Okay. For homogeneity, you just move to other points, and then that point it is the same. Can even you move in any place, it should look the same. So that this kind of thing is just kind of philosophy, but now it just become a principle because the observation also tell us that universe homogeneous and isotropic. So that this is a kind of description. If you go more deeply, maybe mathematically, this kind correspond to rotational invariant, and then this is translational invariant. This is the basic thing you need to know. But this is quite powerful symmetry you can use in when you try to apply to Einstein field equations. Okay. So now this is imposed only in T space, not 4-dimensional space-time, because if look at the same in every time, you cannot have the dynamics, right? So that we need the dynamics so that this kind of thing just solely on T space. In this case, you can make like Ajahn Pichet tell you have a kind of box, and then you slide whatever you slide, and then you can take this one is just T time constant, and then in cosmology you have the time is just you have separate time to the T space. For example, this kind of thing is just TD. And then in this TD, you have a kind of this symmetry. And then if you have a kind of this symmetry, you can decompose the matrix. Okay, this is just T space. On this, the fixed T, you have this one. And then you have what we call scale factor to factor this T space. And then this T space, you can write it like a, okay. What notations I use? Okay. Let me put in this way. The sigma to okay. It's just T space. Gamma is just metric on this surface. So now you have the thing you know on this surface. When you try to put symmetry, you put symmetry on this, and then they have a kind of spatial matrix or spatial spacetime that we call maximally symmetric spacetime. What does it mean? It means that in that kind of spacetime, you have the number degree of freedom of the matrix, which equal to the number degree of freedom of the constraint. For example, if you have symmetry translation in 3 dimensions, you have constraint. You have 3 constraints, right? Maybe x, y, and z. Whatever you go to in that direction is the same. Rotation also in T space you have 3. So that the number of metric here is just 6, right? So that this kind of thing is we call maximally symmetric, because the number of constraint is equal to number of independent component of the matrix. Okay, number degree of freedom. So that in this case, you can write immediately the curvature tensor. For example, you can write you just put it like this. This is just belong to the symmetry of Riemann curvature tensor in 3 dimensions. And then if you have something like this, you have only one constant to determine the curvature of space-time, because this is the matrix already. And then the curvature contains only on the number k here. Okay, so that you, in this case, you can know what Ricci tensor, which is in n dimension, if I remember well, is a kind of like this. And if you try to find r, it's just n, and this should be k also. In my lecture notes, I have derived this. You can find it. Okay, so that in this case, you can solve for the matrix here. How can you solve? You just know that this one equal to this one, right? And then you you can use the metric that you know before. So you have spherical symmetry, so that you can write the general form of the metric tensor. And then you can find this one, right? You just take find the connection, and then you can find the Ricci tensor, so that you can solve this equation. Because if you put this one, you can have the differential equation for alpha, and then you can get solution like this. Okay. I use in another, but in this case, if you make it the same, so that the final matrix So this kind of thing known as FL W matrix. This is the metric that you use to describe the dynamics of the universe. And then this constant, this space-time or this space, for example, can be characterized in TKS, K equal to 0. In this case, you get flat metric, right? Flat on T space, so that this is a kind of flat. If K become negative, or I put just a number, what, -1, this kind of thing I suppose to open, I'm not remember well, but you can see in my note, it's a positive. Now I put this part 1, it just close. So this is the basic thing you need to know. So now Einstein field equation. You have one. Oh, I forgot scale factor. You have one function to determine and one constant to determine what this kind of space-time you have to determine this one. You have to determine from which equation. You have to determine to Einstein field equation, right? You have to put it in. If you have the metric like this, okay. In GR, you have one more equations, right? In the left hand side, if you put this matrix, you will find the derivative of the scale factor, right? In principle. And then this one, you need to know first what this is. And in cosmology, we assume that, no, we not assume, we assume cosmological principle already. So that the matter or the fluid in this side need to be kind of perfect fluids. What is a perfect fluid? It is the fluid that you determine by density and pressure, only two functions. You can determine it. And for the cosmological principle, you need to put its only T, depend on so only T, the time. So that in this case, you have relation between this one to this one, right? In differential equations. And then you have one more equation, it's come from the matter itself. That is the conservation of energy momentum tensor. So that this equation you need to solve. Okay. And now I think it's the time to solve this one. You put on Einstein field, maybe this equation first. I have detailed calculation in my note. Rho dot S. Rho dot. Dot is the derivative with respect to times. Okay, this is the equations you have from here. And for Einstein field equations, you have only two independent equations, which is kappa นี่ use K นะ so in my note I rescale K to be kappa, but it did the same. It just tell you what kind of space you have. So you have only this equation. This come from Einstein field equations, and this come from conservation equation. And then your task is just solve this. So now you have three function, right? Scale factor, and density, and the pressure. So that you have three equation. You have three variable to solve. So that in principle you can solve, right? But it's not independent. For example, this you can find these two combination, you can get this kind of thing. So that in principle you have only two independent equations and three variable. So that you need to put more constraint or put more assumption. So that in this assumption, yes,ใช่ไหมวะ P equal to W rho, I think. Pressure is equal to the parameter rho here. Okay, in this case, you just put it in and so, right? If you put in this case, oh, H, what is H? Is it? H. Hubble parameter, and then this isถูกไหมนะมีสามป่าวะ Okay. Okay. Now we can solve this one. Rho in term of A, right? This is just A dot over A. So that in this case you can solve okay. This is you can solve it. So that you put this one into this one, you can get scale factor in terms of time, right? And then you put it back, you will get you can get the closed solutions. And then this closed solution depend on K, right? How it's K. So that in this case, you can solve for K equal to 0. In this case, it's easy. And then you will get a proportional to T. Let me general solution. So okay. So that you can know what exactly rho depend on time, pressure depend on time, and scale factor depend on time for flat space. If non-flat, it is still possible to solve, but it's quite difficult. You can do in exercise if you want. But now, if you try to make the dynamics of the universe, you can combine these two equations. And then you will get the acceleration equations. Okay, it's correct. So you will see that if you put normal matter, for example, what we call in cosmology dust. Dust is a kind of thing that is a molecule of the gas that no have interactions. No have interaction. What I mean is just they don't collision together. So that this kind of thing give you a pressureless, right? Because it doesn't move anymore. Actually, it moves, but it's very slowly. So that in this case, W equal to 0. And if you have radiations, W equal to 1/3. So that in this case, you can put and you will see that the universe not accelerate anymore. It just deaccelerate, right? Normal matter. A is double dot solve less than 0, right? Actually, it makes sense from Einstein field equations. If you have mass, and then every mass contract together, right? So that somehow in the universe start to be synced in this case, so that it not accelerate anymore, but it sync. So that you can imagine from this equation. And this is a kind of thing in cosmology. You just find the dynamics of the universe. And this is the basic equation you need to solve. Yes, these three equations. But on the observations, we know that the universe expands with acceleration, right? So that in that case, you have to make so that W need to be less than minus 1/3. So that this is these are the main tasks of cosmology is just find the consistent matter or modify gravity that correspond to this kind of thing. Actually, from the observations, this kind of thing is mostly equal to -1. So that this is the task. Okay, and this is almost done now. What we go further? Okay, I will go what is the picture of the universe from the observation nowadays. As we know, we have acceleration in the very beginning of time. We call inflation, and then nowadays. And the matter that make universe accelerate in the nowadays, we don't know what it is, and then we call it dark energy. So that it is the whole thing for cosmology. Cause we just try to figure out what make universe expand accelerate. So nowadays we have observation that suggest the universe expand with acceleration. But in the early universe, how we know? Why we know that the universe at the beginning, maybe not beginning, it just very early, tend to -45. This kind of thing second somehow inflation take place at that time. It's the very beginning of the universe. So that why we know? We know from the puzzle. The puzzle we have, like nowadays, we know that. Okay, we know that the curvature here approximately 0. So that this kind of really flat. Okay, and then if you define omega, it just kind of roll over you define what they call density parameter, I think. Yeah. If you define like this and you recalculation this equation in terms of this parameter, you will get put into Einstein field equation and use that equation, you will get what this equation tell you? Prime is just derivative dn. N is just log a. Okay. So that this is a kind of parameter. If you know the scale factor, if you know t, you know scale factor, right? And then you can make it to take log, and then in this equation become like this. What equation this equation tell you is tell you that this one have a fixed point at 1, right? What you mean fixed point? Fixed point, if you put omega equal to 1 exactly, there are no dynamics, right? But if you perturb it, I mean, make it small oscillations on this, is a okay. หวังว่าจะไม่ได้ใช้ This kind of thing is just what we call it just unstable fixed point, because if you put it here, positive, it need to be positive, right? Omega is a density. If it's positive, omega is increasing function. So that in that kind of thing, you have omega here, and then you have 1 here, is a kind of thing like this. Is divert from omega to 1, right? In this case. Okay, what does it mean? It means that if you perturb omega in the early universe, they are diverse to another kind of thing, so that omega may be 0 and then infinity at this time, at the present time. So the puzzle is that why the universe so fat in nowadays, in the present time. If you need omega to be equal to 1, you need to tune at the beginning. For example, you have nucleosynthesis. I don't remember how long is it, but you can see in the lecture notes. You have to tune like a omega nucleo. It's about 1 plus and minus. You have to tune to 12 digits to get exactly compared to observation nowadays. So that this kind of thing is just tuning problem. You need to tune at the initial condition, and the puzzle is just why the universe so fat nowadays. This is just a kind of puzzle, right? It's not matched with the observations. Other thing is we call horizon problem. I will give you until T30 because I come late. You come late. Okay. Okay, I have 20 minutes left. I have to go more quickly so that horizon problem. Is it a kind of when you try to see the light in the path, how it's come to us? So that in this case, you just use the new geodesics of the light at that time, and then how it's come to here. I take the diagram directly. The kind of thing is just tau. Tau is proper time. It defined like d tau is equal to a dt somehow. We call proper time. And then if you draw the space-time diagram for this, for example, at nucleosynthesis or recombinations. Why recombination is just because we can see the light, the last scattering surface at that time, the time that we see cosmic background microwaves or CMB here. So that in this case, if you have light from here and travel in the light cone to us here, and then you take it back, how the light can be travel in the past before recombinations. It's just very small area here. If you can calculate it, so that the question is, if you have if you have two points in the space time, for example, you can see 2 points when you look at in the space, and then you will see that it's just about 1 degree that this area can make. I mean, if you consider 2 points here and here, it is only 1 degree over here and 1 degree over here. Light can travel. It means that light from here and light from here are not causal connected, because if they want to go to this part, they have to take more time. So that in that case, we call that the light cannot be in the same place anymore. It's not possible to have light in the same place. And then what is the problem? The problem is just what we see from CMB temperature is it's about 10-5. It's almost the same temperature. So that why the light in different places have the same temperature. All right. This is also called horizon problem. And then in this case, both of case, if you make it 3 in this case, also in this case, if you make like that, it means that they have the inflations. The inflation is just enormous acceleration at the path, right? So that this make light cone in the path causal connects here. It means that usually you just know that 2 points are not in the same place. So that if they have inflations, you can tell that, oh, they have in the same place before, but inflation make it separate together. So that this is a kind of puzzle you can solve by take the inflations. In mathematical calculation, you can see in my note. So the dark energy, for dark energy, just in the same, we know that the universe expands with acceleration. So that we need to put something that make it accelerate. So now we try to consider the inflation first. For inflation, you need the dynamics, so that you have to put more thing into Einstein field equations or matter. Yeah, okay, good. This is a kind of scalar field. Why scalar field? Is the first model, right? You have the simple one, so that you put scalar field, normal scalar fields into this. When you put scalar field, you have energy. You can find the energy momentum tensor. So if you have action for scalar field, maybe okay. It's just kinetic term and potential term, and you add into Einstein-Hilbert action, and you vary this one with respect to the metrics. I think maybe you can do in homeworks. You will get okay. This is maybe the definitions of the energy momentum tensor, and you will get for scalar field. Okay. And G mu nu. Okay, it's something like this. So you have a you have an equation, and you put it into a Einstein field equation, and you solve it. And you will see that. Come back again. Row. And then. Okay. In this case, rho is equal to is I remember well. This is plus, this is minus. Okay. Okay. And then you just show it. Oh. I don't remember well. If you want to define parameter in inflations, you need to make the accelerations equation is about something, and then this is just and you define this parameter epsilon, we call the low parameter, is equal to minus h dot s square, like this. if epsilon go to 0, the universe will expand with acceleration, right? So that this kind of thing like makes slow, the parameter that take care of the inflations. Also, if you need to have long enough inflation, you need more other parameter. Usually, maybe they call eta is a kind of epsilon over epsilon. Prime is just derivative with respect to n here over there. That is the way you can use. Actually, this kind of thing then this kind of thing approximate 0 is turned out that phi dot less than much less than potentials. And this kind of thing tell you, and then much less than something. Okay, about this one, I don't remember well, but you can derive. Actually, you can find in my note. The kinetic term need to be subdominant. Also, the accelerations of acceleration of the field need to be small compared to the this kind of thing. What we call phi. This kind of thing correspond to make it slower than make the field slower. What we call whatever that kind of thing. I don't remember the word. Viscosity, right? Okay, this is a kind of viscosity term. So that viscosity term have to be dominant compared to the acceleration. So what we need is just if you need the scalar field have less dynamics. So that from this equation, you can see that these terms have this kind of potential control the dynamics, right? For example, if the potential is quite flat, if you put scalar field, it moves slowly, right? If the potential is really deep, this is quite fast, right? So that this kind of thing just tell you from the potentials. Actually, from this, you can derive how the potential is. The first epsilon is depend on, if I remember well, and then eta is depend on oh, I don't remember well, but depend on like this. This is the first the slope of the potential. This is a kind of make the slope of the potentials long enough. And this kind of potentials, something like this. Okay, I can put it here. Oh, put that. Okay, background. Okay, you have flat potentials here, and you put scalar field slow during this the inflation occur, and then this is the slope quite a lot, right? So that this is inflation can end at this point, and then if they have some minimum of the potential, the inflaton can oscillate here. And when the photon oscillate here, This is a kind of reheating. Okay, I will summarize like this. You can put scalar field in terms of inflations, or you can put more term in kind of modified gravity. It's somehow equivalent to the scalar. You put scalar fields. Actually, if you saw the equations, this kind of we know as a Star-Rubinsky model, the kind of inflationary model. For dark energy is, I can summarize like this. You cannot use this kind of potential because when you consider dark energy, you need the universe have matter dominate and radiation dominates, right? So that in that case, the potentials, I do not put in my note because I don't have enough time. In this case, I will modify the note if I have time. V phi is somehow like this. Lambda need to be small. Lambda. So go to 0. I mean, the slope of the potentials need to be small at the present date. But during inflation or during matter and radiation dominate, is not need to be go to 0 in that case. Yes, if you want to make it different from cosmological constant, I forgot to tell you about cosmological constant, but cosmological constant, just put constant into this one. Maybe two lambda into the actions, and then you can get acceleration also. Okay, this is an overall background we need to clarify in cosmology. And then I have about 10 slides more about the perturbations. Why it's so important? Because if you consider if the space-time have uniform for overall, so that they don't have galaxy, they don't have us, they don't have the star, so that you need perturbations to be original ingredient to make it inhomogeneous in very small scale. So that in this case, you need to go to the perturbations on the black cloud. And I will talk on the perturbation about maybe 2 minutes. Okay, for the perturbation, it's quite important for inflation because when you go to the inflation, you need the quantum fluctuation during inflation can get seeds of perturbation nowadays, and then you can make the galaxy, you can make other things in small scale. So shiny. Okay, so that this kind of thing you need to do a perturbation like this, the metric. This is a background, and then you put into Einstein field equation here, and then you will see the equation is very complicated because the perturbation depend on space and time, so that is impossible to solve it. You need to decompose the variable into T category. The first scalar mode, and second is vector mode and tensor mode. why we separate like this? Because if you separate like this, the equation of motion is just decoupled, so that you can solve part by part, and then it's easy to not easy. You can do it for the vector mode. You will see that in my note. They are decay, so that they not exist anymore because it's decay. And then you need to compute only scalar mode, which is a kind of inflaton. And then the gravitational wave also get it from during inflations. Here, it's just the way you can compute it. I just suggest you. And then when you compute it as Palm, Ajahn Palm tell you, they have gates. For example, if you choose the gate that not improper, so that's one is not physical thing. You need to choose, or you need to do okay. You have to use gate invariance, and then in lecture notes I give you how to construct this kind of gate invariant variable, and then you have another options. You just choose the gates. For example, you choose something to be 0 immediately, and then compute the other, which gate have advantage in some situation. You can choose it. So in the note you will see which one is approximate, which one is proper when you use for each situation. So that I also put it when you compute the perturbation. You have to the perturbation of the energy momentum tensor, and here you can define what we call adiabatic perturbation, entropy perturbation. And then they have the key thing when you compute, for example, scalar fields during the inflation. During inflation, they oscillate, right? When they oscillate, they make a perturbation because they have sometimes yes, the amplitude that's not the same, right? But when they get out from the Hubble radius, they get out for some scale, it's fixed. So that when it fixed, it means that the perturbation during inflation will fix, and then it come later on. For example, is when it come, the perturbation come to the horizon during CMB era, or decouple last scattering surface. For example, you will get the perturbations which is in very, very high energy scale in the CMB. That is a good thing for to make link between observation and theory. And I also put what I put is just when you compute it. If, for example, you can try to modify the theory. Here I put a general form of the scalar field, which is x is kinetic term, and then you compute second order perturbation here. Instead of you compute the equation of motion, you can compute on the level of Lagrangian or action. In this case, you will get the same equation of motion, but you will know the structure of the theory more. For example, this one, as Pichet tell you, maybe it get the instability, because if this kind of thing is negative, it will call instability or code. If you have to put no code condition, and then also this kind of thing we can call Laplacian and instability. So that in this case, it make you know also the stability of the theory. And then I think other lecture they will try to construct more general scalar vector tensor theory, and then consider how the perturbation does not give you more degree of freedom that has a cause or instability. That is the main idea of the school. Khamphee will tell you later. I think, man, ใช่ไหมพี่คัมภีร์ okay, okay. That's it. I put the job on you already. Nah. Okay. Any questions? I stop here.
About when you say that the scalar field doesn't work.
Scalar field doesn't work.
The scalar field, the model of the inflation.
Is
So you drew the graph of so you mentioned the cosmological constant. So that graph you wanted to mean that we cannot use that one scalar field for the whole like inflation and dark energy.
oh yeah, yes, we cannot use it. It's
And
a kind of potential. It's another kind of potentials.
but we can use like two scalar fields like separately for inflation and
Yeah,
dark.
they have some people try to do like that. Yeah, but I think it's many obstacle because when you have end of inflation, you need a scalar field to decay to other matter, right? In that process, you need to take care of another scalar field also. How the law of that scalar field also. It's quite difficult, right? But I think, but they have some people try to do it. Yeah.
So it's kind of like constrained on the boundary or barriogenesis.
Yes. Many constraints actually. I don't know much, but I just know that they have many constraints. That two scalar field doesn't work for both inflation and dark energy. Even dark energy scalar field have to not successful much actually, as I know.
Like I wondering, like I have no idea why we always talk about the scalar field. So I may need more insight, like why we talk about scalar fields, like why not the vector fields or any tensor fields. Like for example, for the inflaton, why do we need it to be scalar?
Okay, that's a good question also. Why we doing scalar field? Maybe the first answer maybe it's easy. Yeah. We try the easy choice first, and if it doesn't work, we go to another choice, more complicated, right? But if you put scale vector field doesn't map with cosmological principle, because if you have vector field, you have direction, you have to prefer, so that is not that violate isotopy condition, rotational invariant. But the people try to do it. You put three scalar field randomly direction something, but it's much more complicated in that case. They also have put vector field, but finally you get the degree of freedom only one, which is just put constraint on that vector fields. Also, people also do. I think maybe they will give you a more general theory they call scalar vector tensor theory. Put all fields into the theory. That's very complicated. And then this is just give you a first thing when you can do in the first place. ทางนู้นหน่อยเดินไม่หน่อยส่งต่อเลยก็ได้ครับ you can pass this, okay?
Yeah, so when we talk about the inflation, we say it will solve the horizon problem.
Yes. Yes.
And my my question is that we say it's problem because 2 point in different direction don't have time to contact each other.
Yes.
Why we propose inflation? Why not we propose that maybe the physics is the same and 2 different distinct point evolve independently and become the same temperature?
Okay. That is good questions. I also think about like this. What you mean is just why is a problem, right? Because you can say that, oh, the nature have the same temperature at the beginning. You can say, right? But if you physicist, you may ask, what is the mechanism that make have the same temperature? Yes, that sometimes people don't call this problem. It's just called a puzzle. It's just theoretical things, but yeah, it's a kind of when you try to tune. For example, this point and this point, right, is far together, and then there are no causal contact together. In principle, they don't need to have the same temperature. But if you put many circle on that thing, maybe this can connect it, right? Maybe, but in that case, you take time more than the age of the universe, far from the age of the universe. So that in that case, it's not possible. We just try to explain how these 2 points have the same temperature, so that it's easy. Actually, these 2 points have the same place before, because inflation make it separately, and then we see this point at this time that inflation makes. That it we imagine that they have a kind of this thing in the very beginning of the universe to explain the observation. Actually, any more questions? I have to go to take my son in the school. So if you have more questions, you can ask me at the tutorial class. Okay, I will stop here. And we have break outside. Still have, right? Okay. See you on the. So you are late for the beginning of my class. So now I give you only 5 minutes break. You just go to the toilet if you want, and then Khamphee will give you an introduction to modified gravity theory.
ใช่ใช่
หนึ่งก่อน
เอาออกก็ได้ดีครับปกติมันอยู่เดี๋ยวไปเรียนไว้บอร์ดครับ
ให้เริ่มเลย
ได้ยัง
นะ
เริ่มเดี๋ยวอะไรนะ เดี๋ยวรอจันสามเข้ามาก่อนเราปิดประตูห้องก่อน เริ่มได้เลย
ได้เลยนะ
ใช่ครับ
ให้ขึ้นเองเลยนะ
ขึ้นเลยเดี๋ยวจะเริ่มบรรยายแล้วนะครับ
Okay, we will start now, I think. In my lecture, I would like to present the basic idea of modified theory of gravity. First, I will give some motivation for modified theory of gravity, and then I will briefly describe how to construct the modified theory of gravity and show you some example of modified theory of gravity, such as the gravity theory that gravitational interaction mediated by extra field in addition to metric tensor, and then the gravity theory that equation of motion contain higher order derivative of metric tensor and minimally modified theory of gravity. Finally, I will briefly give some idea about teleparallel gravity. Okay, the basic motivation for modified gravity theory is based on the following issue. From the observation, we know that the universe expands with acceleration at late time. Moreover, to solve the shortcoming of the hot Big Bang model, we have to suppose that universe expand with acceleration also in the early time. To describe the cosmic acceleration at early time and late time, we have to introduce the mysterious form of
energy in the case where gravitational interaction obeys the general relativity. So for the late time, we have to introduce dark energy, and for the early time, we have to introduce inflaton. However, the cosmic acceleration can be achieved without introducing the material form of energy if the physics of gravity deviate from Einstein's theory of gravity or general relativity. So the next issue is that in the general relativity, there are the singularity problem. The singularity is the point in the space-time that energy density go to infinite. So, for example, the singularity are the hot Big Bang singularity or singularity in black hole. This singularity can be avoided if we taking into account the effect of quantum gravity when the energy density around that point go to the Planck energy. However, in some sense, the general relativity does not compatible with the quantum theory of gravity because in the simple sense, when we would like to make a quantum theory of the field, in the quantum field theory, we have to quantize the field in the fixed background. I mean the fixed space time. But in general relativity, the space time itself is a dynamical variable. So it's quite clear how to define the quantum operator in this case. Okay, now before we learn how to construct the modified theory of gravity, we have to know the basic assumption for the general relativity. Okay. The construction of general relativity is based on the equivalent principle. For the weak equivalent principle, we can conclude that around the small enough region, effect of gravity cannot be distinguished. The effect of gravity and effect of uniform acceleration cannot be distinguished. So, for this reason, we can define the initial frame such that the gravity disappear by the free falling frame. So, based on this idea, Einstein extend this idea to the general situation where the equivalent principle can be applied to the all law of physics, not only on the law of mechanics. So in this case, for the small enough region, we can define the free falling frame such that the effect of gravity can be ignored and our law of physics obey the special relativity. So this inspired Einstein to link the nature of gravity with the curvature of space-time. For example, we can imagine about the space of arbitrary geometry, arbitrary curve. This space can be identified as a manifold. By definition, manifold is locally flat, mean that if we, for the arbitrary shape of space. If we look at the space at the enough small region, that region can be looked as a flat space time, such flat space, such that the first order derivative of metric tensor varies, something like that. So you see that we can define the flat space locally on the curve manifold with arbitrary shape. This is quite similar to the Einstein equilibrium principle, such that we can define the local invariant, local inertial frame at some particular point only. And when we try to transform each inertial frame at particular point to another point in the curved space-time, we can mimic the effect of gravity, something like this. Now we have manifold to describe the physics phenomena. We have to introduce the field into this manifold. The field can be a scalar field, vector field, and tensor field. So, which can use to describe the physical quantity. So, in this case, I would like to talk about the vector field a little bit. Vector field that defined on manifold is different from the vector in the sense of classical mechanics. In the classical mechanics, vector can be defined as can be viewed as a direction of the particle that move from one point to another point. But on the manifold, vector is defined at particular point. And okay, to compare two vector, for example, the vector at point A and vector at point B, we have to move vector at point B, at point A to point B, and then compare vector A and vector B. Moving of vector A along some curve from point A to point B can be performed using the parallel transport, which define from the affine connection. The affine connection is the connection that used to define the covariant derivative. As you know, the partial derivative of tensor field does not transform as a tensor. So to make the derivative of tensor transform as a tensor, we have to add the correction term to the partial derivative. This correction term is called the connection. In this case, it's a affine connection to state that this connection does not depend on metric in general. Okay, now we know how to move tensor along the curve. I mean, we know how to describe the dynamic, right? Because physics, in the physics theory, we would like to know the dynamic of the object move in some direction, or how to change when the time change, how the system change when the time change. So we have to know how to the physical object move along the curve, blah, blah, blah. So now we to define the length of the curve or the length of the vector field, we have to define metric tensor, because as you know, the scalar product is defined from the metric tensor in the curved space-time. So now we have manifold, an object on the manifold which describe the physical quantity, and connection and metric tensor that have the different role in the curved manifold. Now we come to the basic assumption of general relativity. The basic assumption is that the connection in general relativity is the Levi-Civita connection or Kitafo symbol. In this case, the connection can be defined from the metric tensor. To obtain the relation in the first equation on this slide, we also have to assume that the covalent derivative of the metric tensor varies and the lower indices of the connection are symmetric. The geometry that described by manifold and metric tensor only is a Riemannian geometry, and Einstein theory is formulated on this geometry. Another condition for the general relativity is that the gravitational interaction mediated by metric tensor only. Okay, now to find a list of to find the list of conditions that we need to impose for the construction of the modified theory of gravity, we come to the Lovelock theorem. Now we consider the metric theory of gravity. The metric theory of gravity means that the gravitational interaction described solely by the metric tensor. As I mentioned, in general, the affine connection and metric are independent, but in the metric theory of gravity, connection can be computed from metric tensor, or we consider only the Kitafo connection that is the Kitafo symbol. Now, based on the Lovelock theorem, any gravity theory construct in 4 dimensions from the action principle in which the action contains the metric and derivative of metric tensor always produce the equation of motion that contain up to second order derivative of the metric tensor, and the equation of motion take the form of Einstein equation only. So in this case, in order to construct the modified theory of gravity, we have to break some assumption in Lovelock theory. Some assumption that used to derive Lovelock theorem. So if we break the condition in the Lovelock theorem, we can get the equation of motion for gravity that different from Einstein equation. This is the idea. Okay, for this reason, we can construct the modified theory of gravity by do at least okay, by do the following procedure. First, we can add the extra field to describe gravitational interaction, or we can allow the equation of motion to contain higher order derivative of the metric tensor, or we construct the theory of gravity in the space-time whose dimension is different from 4, or we suppose that the gravitational interaction mediated by tensor which is not a rank to 0 tensor or metric tensor, or we impose some symmetry in the equation of motion. Now we consider the first class of the modified theory of gravity, in which the gravitational interaction mediated by additional field or extra field in additional to metric tensor. This modified theory of gravity have a long have motivated for long time ago. Perhaps it start from the Dirac assumption. I forgot the year, but Dirac have noticed that the ratio of electromagnetic force to the ratio of gravity force and the ratio of time scale related to the electromagnetic and age of universe is large but are comparable in magnitude. So they like think that this should not be the coincidence. So for this reason he created the hypothesis that Newton gravitational constant is not the constant but can vary in time. And around the year 1960, Benedict test this feature of gravitational constant again by construct the theory of gravity in which the gravitational constant depend on the scalar field. Okay, the gravity action for the Benedict theory can be written in the form shown in the first equation on the slide. Here we use the unit where 1 over square root minus 1 over square root 8 pi g equal to 1. And here field alpha is scalar field and psi is a constant. R is the scalar. Okay, compare this action with the compare this Lagrangian with the Lagrangian for Einstein-Hilbert. We can define the effective gravitational constant as shown in the second equation. You see that because scalar field have dynamic, so in this case, the gravitational constant, okay, the effective gravitational constant is not constant but depend on the field, which depend on time. Actually, this action also motivate from the Mach principle, which state that the law of physics should depend on the environment, something like that. But okay. Okay, in the action there are the term which is the multiplication of the field phi square with the Ricci scalar. This term describes the non-minimal coupling between the scalar field and gravity. Okay. Due to this term, the scalar field become a part of gravitational interaction. As you see now, the gravitational constant depend also on scalar field. So, and for this case, gravitational interaction mediated by scalar field and metric tensor. And compare with the Einstein theory of gravity, general relativity, the propagating degree freedom of gravity in the Einstein theory is 2, come from the 2 polarization mode of gravitational wave. So now we add the scalar field into the gravitational interaction. So scalar field have 1 degree freedom. So totally we have 3 degree freedom 3 propagating degree freedom of gravity in this theory. This theory is a scalar tensor theory of gravity. Scalar tensor means the gravitational attraction mediated by both scalar and tensor. Now we from the action of Bandit theorem, we write from the Lagrangian of the Bandit theorem shown in the previous slide. We write the action for the Bandit theorem as shown in the first equation on this slide. And then vary this action with respect to the metric tensor. We get the equation of motion shown in the second bullet. Here, T mu mu matter is the energy momentum tensor of matter, and T mu mu phi is the energy momentum tensor of the field phi. From the equation of motion, you can see that the equation of motion for this theory contain up to the second order derivative of the field. So I would like to state here because it's quite important in a later issue, later discussion. Okay, in the equation of motion, we have defined a new field or phi, and the energy momentum tensor is defined as usual. The relation energy momentum tensor can be defined as a fractional derivative of the Lagrangian with respect to the metric tensor. Actually, this is not much important. I just show you for the for example. Now we apply the covariant derivative to the equation of motion from the previous slide. We obtain the equation in the second bullet. From you see that for the even though we add the scalar field and minimally coupling the scalar field to the curvature tensor, the conservation of energy momentum for matter still concept as still hold. I mean that the covariant derivative of the energy momentum tensor of matter field also valid. This is the conservation of the energy momentum tensor. So this means that if we consider the small enough region such that the first order derivative of metric tensor valid, I mean the space look locally flat, the covariant derivative become the partial derivative and Ricci scalar valid. So we get the conservation in the Minkowski scale, Minkowski space time. I mean the covariant derivative become the partial derivative. So we get Naba. First we get Naba T mu mu in the curved space, and then we look locally at the locally point. We get partial mu T mu mu, and these both are valid. So this means that the weak equivalent principle also hold in this case. Now we consider the generalization of Bandit theory. The Bandit theory can be simply generalized to the case where the non-minimal coupling term replaced by f arbitrary function of field and its kinetic term. So replacing phi square r by f of field and x. Okay, now may I take a break a little bit? I'm sorry, my laptop have a low battery. Wait a little bit.เอาที่ชาร์จตรงนี้ไว้ เข้าแล้วแป๊บนึง Okay, sorry. To build the general theory of modified theory of gravity, we have to carefully concern about the ghost and osteogachy instability. In a very simple sense, ghost occur when the kinetic term of the dynamical variable have the wrong sign. For example, x is a kinetic term of scalar field. Usually, it's a kinetic term of scalar field proportional to the field dot square dot is derivative with respect to time. But God appear when the kinetic term depend on minus field dot square. Okay, in this case, the Hamiltonian, which is the kinetic plus x plus the potential term, can be negative. This negative value of the Hamiltonian is not similar to the negative due to the reference, due to the choice of the reference point of the potential. But now the negative of the Hamiltonian come from the negative contribution from the kinetic term. Now we can say that the system always evolve to the configuration where the total energy is minimum. Now you see that there are no minimum for the Hamiltonian because the Hamiltonian can be largely negative or can be minus infinity if the kinetic term absolute value of phi dot is large. So we, in this case, the system evolve, never stop, something like that. Know the stable point, know the equilibrium point. So in this sense, we can say that there are instability. There is an instability when the ghost appear. Now we discuss about the briefly discuss about the Ostochasky instability. The Ostochasky instability appear when the equation of motion for the uh, for the dynamical variable depend on time derivative that higher than 2 order 2. If this term appear, the momentum, the Hamiltonian can depend on, okay, if this situation appear, the momentum can depend linearly on conjugate momentum of some dynamical variable. As you know, the Hamiltonian usually depend on the momentum square. Now, if there are the higher order derivative, time derivative of dynamical variable, the momentum, the Hamiltonian can depend on so now order derivative up to the first order derivative, the motion contain up to the first order derivative. This follow from the Euler-Lagrange equation. And as I mentioned, the higher order derivative of the dynamical variable lead to the Ostochasky stability. So, but for the stability of the second order derivative of the Lagrangian, the motion theory can contain up to second derivative for the Ostochasky stability. This theory can be constructed suppose that the Lagrangian invariant under the chip symmetry, under the chip, under the transformation shown in the last bullet. This transformation called chip transformation. So okay, as scalar field theory which have a chip symmetry is a Karwan theory. Okay, here for example, I show you the example of Karwan, example of the Lagrangian for the Karwan theory. In this expression epsilon is a total Levi symmetric tensor, and L4 mean that there are 4 scalar fields in this theory. There are 4 scalar fields that multiply together. But The Galilean theory that I showed, the Lagrangian, is the Galilean theory in the flat space-time, in Minkowski space-time. To generalize Galilean theory to the curved space-time, we performed the usual covariantization by replace the spatial derivative by the covariant derivative. But this simple covariantization is not enough, because when we replace partial derivative with the covariant derivative, there are the terms that contain the higher order derivative of the metric tensor in the equation of motion, contain the term that depend on higher order derivative of metric tensor in the equation of motion. Sorry, So to cancel this higher order derivative term, we have to add the correction term to the theory. And finally, people can derive the Hodgsky theorem from the Galilean theory. Can derive the Hodgsky theory from the Galilean theory. Around 1920, Hodgsky derived the general form of scalar tensor theory using his assumption, but now we can also derive the Hodgsky theory from the Galilean theory by perform the suitable covariantization. Here I just list the form of Lagrangian to show you a little bit, not really important. Now, there are another way to construct the general scalar tensor theory of gravity. This based on the degeneracy of the Lagrangian. Okay, let us consider the Lagrangian which contain the Q1 dot square and Q2 dot is a linear, but Q1 dot is a quadratic. So, and when we use the Euler-Lagrange equation, we see that the conjugate momentum P2 of the Q2 constant. So this means that P2 is a constraint of this system. And when constraint appear, you see that we get constraint equation such that the partial derivative of potential with respect to Q2 varies. This give the relation between Q1 and Q2. This is a constraint equation, not equation of motion. And now we have the relation between Q2 and Q1. In general, if we have such condition, we have condition among the dynamical variable, we can use this relation to reduce the degree of freedom, number of degree freedom of the system. For example, we have imagine that we have a Lagrangian which depend on Q1, Q2, and Q3, but for Q2, we have when we vary action with respect to Q2 and we obtain the constraint equation, we have the relation between Q1 and Q2 and Q3. So the dynamical degree freedom, number of the dynamical degree freedom is not 3, but just 2. I mean, independent dynamical degree freedom is not 3 but 2, because we have constraint equation that relate one degree freedom to another. For this reason, okay, using the constraint equation, one can reduce the order of time derivative in equation of motion, because the order of time derivative in equation of motion also represent the number of degree freedom in the theory I Actually, I have to briefly discuss about this a little bit, but okay, I skip because I did not prepare for this. Now, in this case, uh, when 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 the Lagrangian depend linearly on time derivative of some degree freedom, the Lagrangian will produce the constraint equation, and the Lagrangian which have this property is called the degenerate Lagrangian. So, because degenerate Lagrangian depend linearly on time derivative of some degree freedom, we can define the degenerate Lagrangian using the condition shown in the next slide, determinant of the hegemonic values. By impose the generality condition on the Lagrangian, the most general scalar tensor theory in 4 dimensions can be derived. This theory is called degenerate higher order scalar tensor of gravity, or the host. We can have a look at the action a little bit. Action consists of 3 parts. The first part is that non-minimal coupling term, and the second part, Li2, is the piece of Lagrangian quadratic in second order derivative of scalar field, and the third, the last part, L3I, is the piece of Lagrangian quadratic depend on the second order derivative of scalar field. As you see, the Lagrangian of this theory quite complicated, but based on the current constraint on the propagation speed of the gravitational wave, this theory is tightly constrained. But I not talk about this. Professor David Mota talk mentioned about this in his lecture. Very complicated theory. Oh, okay. Now we come to the theory of gravity that contain the higher order derivative in equation motion. This theory, originally this theory is construct for searching the theory of gravity that can be renormalized. Yes, but up to my understanding, not very success. But this theory received a lot of attention again when after the discovery of the cosmic acceleration at late time, because this kind of theory can lead to the acceleration of the universe. Because note that this kind of theory may encounter the ghost and also Kaji instability because of the higher order derivative term. But some theory and this card is free from such stability. So, for example, the theory that free from those instability is the popular modified theory of gravity called FR gravity. FR gravity is the action for FR gravity giving okay the Lagrangian for the FR gravity shown in the first equation on the slide. Here F is arbitrary function of Ricci scalar. So variation of this action with respect to metric tensor, we obtain the equation of motion shown in the second bullet. You see that the equation of motion contains the higher order derivative of metric tensor. Okay. You can see that the last two terms on the left hand side of this equation contain the fourth order derivative of metric tensor. So, but it has been shown that this theory free from the both code and also static instability. To show this is quite complicated, but it has been suggested that under the suitable redefinition of suitable definition of the field variable and written the action in suitable form, we can show that the higher order derivative disappear because this procedure is quite simple. I show you here. So we write the Lagrangian in the form shown in the first bullet using the scalar field chi. Sometimes I use the word action and Lagrangian interchangeably, but okay, because when light action in the slide is not too long, it's too long, not so good. So the action in the first bullet with respect to field chi, we get the constraint equation shown in the second bullet. You see that if f subscript r denote the derivative of function f with respect to r, and f subscript r means the second order derivative of the function f with respect to r. So if r not valid, the constraint equation show that chi should equal to mass equal to the Ricci scalar, and when we insert this condition chi equal to Ricci scalar into the original action, we get the action for FR gravity. For the FR gravity, the condition that second order derivative of function f with respect to r not valid, quite general, because if the second order derivative of function f with respect to r valid, we obtain the Einstein theory of gravity. So now we define the field phi as shown on the slide. If we define field in terms of the new field variable, we can write the action in the form shown in the next slide. So you see that is become the scalar tensor theory of gravity. There are two advantages of this expansion of this analysis. So first is I show you that the FR gravity are equivalent to the FR, to the scalar tensor theory, and for this reason, the higher order derivative appear in the FR gravity should not lead to the instability in principle, but when people try to show that there are no instability in FR gravity theory, they do not perform like this, but they use the Hamiltonian analysis or something that quite complicated. Okay, actually, I actually there are two type of modified theory of gravity, but I have no time left, so I talk about the only one, the minimally modified theory of gravity. This theory start from the question that how to construct modified theory of gravity that propagate only to degree freedom similar to the Einstein theory of gravity. As I show you, to construct the modified theory of gravity, we have to add extra field or add additional degree freedom for gravity. For example, scalar tensor theory, we have the scalar degree freedom for gravity. Now, why people ask this question? Because when there are extra degree freedom in modified gravity theory, we have to cancel or separate effect of that degree freedom in some region. Because, for example, in the region of solar system, the general relativity is well tested. So this means that there are no. This means that the gravitational attraction are mediated by only 2 degree freedom from the tensor mode. So this, for this reason, we need the mechanism to cancel additional degree freedom in the scalar tensor theory or FR gravity. Is called scaling mechanism. But for this reason and some more reason, people ask how to construct the modified theory of gravity, which have only 2 degree freedom similar to general relativity. To construct this modified theory of gravity, we have to consider the Hamiltonian of the gravity theory. To construct the Hamiltonian of gravity theory, we have to slide the 4-dimensional space-time to the space-like hypersurface that defined from some normal vector, and on that space-like hypersurface is convenient to decompose metric in terms of the ADM metric. Here in is the function Ni is a SHEAP vector and Hij is the metric induced on the three-dimensional hypersurface. Hij is the projection of the metric tensor in 4 dimensions on the hypersurface using the projection operator pi, capital pi, and pi defined from the normal, the pi defined from the vector normal to the hypersurface. And now, in terms of the AD metric, we can write the Lagrangian for the general relativity in the form shown in the first slide. The Lagrangian depend on the function SHEAP vector h and time derivative of h. So there are 3 of dynamical variable n, ni, and hij. So we compute to find the Hamiltonian, we compute the momentum conjugate to these 3 dynamical variable. Because the Lagrangian do not depend on the time derivative of the function and SHEAP vector, the momentum conjugate to this variable are the constraint quantity. Hamiltonian by impose the Lagrangian multiplier as shown in the second bullet. Pi I is multiplied by the Lagrangian multiplier, and pi n, which is the conjugate momentum of lab function, also multiplied by the Lagrange multiplier to represent that this is a constant quantity. Okay, here H0 and Hi is a Hamiltonian and momentum constant that we will show later why this is a constant. As the Pichet mentioned, the constant have to be time independent. So the constancy of the constant pi I and pi n lead to additional constant pi H0 and Hi equal to weakly valid. I'm not sure. I think Pichet also mentioned about the weakly valid because at that time I do something, so I'm not sure. Weakly valid means the valid on the hypersurface, on the constant hypersurface. Now, in conclude, we have the constant pi n, which is the conjugate momentum of lab function, pi I, which is the conjugate momentum of SHEAP vector, and H0 and Hi, which is the Hamiltonian and momentum constant. And from the further analysis, one can show that these constants are the first class, because the first class constant can eliminate 1 degree freedom. So the total propagating degree freedom in general relativity is 10. 10 come from the number of dynamical variable, because the metric tensor is in 4 dimension is a 4x4 metric, and because it's symmetric, so there are 10 variable that used to describe the metric. So now we have 10, and pi n have one constant, so -1, and pi I have a 3 constant because I run from 1 to 3, and H also have a 1 constant, so -1, and Hi have a 3 constant, -3, so totally we have 2 degree freedom. But for the scalar tensor theory, the Hamiltonian constant H0 also depend on the lab function. The consistency relation for the pi n lead to another constant derivative of n multiplied by S0 with respect to n have to be weakly valid. So in this case, we have to define a new constant. The Hamiltonian constant is H0 have to be replaced by H0 tilde, we define in the on the slide. Nevertheless, if we compute the boson bracket between the pi n and new constant, we find that pi n and new constant are second class. So this means that now we count the degree freedom start from 10, because second class constant can eliminate only half degree freedom. So 10 minus 1 over 2, which come from the pi n, and minus 3 from the visible constraint from pi I and minus 1 over 2 visible from the constraint h tilde 0 and minus 3. So totally we have 3 degree freedom. So for this reason, the minimally modified theory of gravity, the total Hamiltonian should contain linearly on the left function. Or in this case, the Hamiltonian, the thing that equivalent to Hamiltonian constraint S0 should not depend on the left function. This is the possible condition for constructing the minimally modified theory of gravity. For this reason, the Hamiltonian of the minimally modified theory of gravity can be written as shown in the slide. HT here cal H0 must not depend on the lab function. And the constraint, the new constraint called H0 in conclusion should not depend on the lab function, and of course should not be the Hamiltonian constraint in general relativity. Otherwise we obtain the general relativity. And example of the constraint cal H0 is shown on the slide. Cal H0 can be the general function of the Hamiltonian constraint in general relativity. This theory is called FH gravity. Okay, but there are the important problem in minimally modified theory of gravity. The minimally modified theory of gravity that I discussed is constructed in the vacuum. But if we add the matter field into this theory, the Hamiltonian constraint become the second class. So as I mentioned earlier, we require the Hamiltonian constraint to be the first class. Otherwise, the degree freedom are not two. Total propagating degree freedom not two. But now, if we try to construct minimally modified theory of gravity in vacuum, and then it's okay. And then after we add the matter field, the Hamiltonian constraint now is not the second card. It's not the first card, but become the second card. So the degree freedom change. To fix this matter coupling problem, we have to add the gate physics term that make the Hamiltonian constraint cal S0 second card in vacuum. If the Hamiltonian constraint second card and the gate physics term is second card, last yes. Actually, we have I have more, but I have to leave. I have to leave. We have to leave. Yes. ตอนนี้แค่5 โมงแล้วใช่ไหม5 โมง 15ใช่ไหม
จบสไลด์
Okay, this is a sample of gate fixing term. Okay, and finish. Actually, finish. If you go to the next slide, is another type of modify. And yes. Later, when I think.
ไอ้ที่ชา
นี่จัดโอเคผมนะ
Okay, if no more questions, actually, you have question. Simple one.
การผิดครับอ่ะแต้มถามว่าต้องเก็บใบเสร็จอะไรแบบนั้นเก็บอะไรมาไม่รู้ว่าแต้มหมายถึงอะไร
Maybe I missed the first part, so I want to know like what is the purpose of modified gravity theory? Like what is the aim for what is the aim for this modification? What do we aim for?
Ah, okay. First, okay. The recently they got a lot of attention because there is a possible candidate for the cosmic acceleration. Yeah, because if we assume that the gravity obey the general relativity, we have to add mysterious form of energy to drive acceleration. But we can, if the physics of gravity deviate from Einstein theory, we can describe the acceleration of the universe. And as as you know, now we don't have quantum theory of gravity. When we, because of the Einstein theory cannot provide that. So the best way is to explore the possible theory of or possible alternative theory of gravity by hoping that we can get some hints for the quantum theory of gravity, something like that.
Okay, I think it's a time to finish this session. We have dinner box, the canteen. Take it and can eat also here, or you can take away. Then we come back again 8:30 for tutorial. And one more thing, as we have to change. We have to change the schedule a little bit because the online thing, so that tomorrow in the morning sections, tomorrow in the morning section, we move we have two slots, right? Morning section. The second section we have talk. And for the session, afternoon session until tutorial is a lecture by Pichet. Whole lecture taking on 5 lecture, so that they include also in the tutorial, so that we don't have tutorial in the for tomorrow. So this lot in the morning, maybe tutorial or for this for today. And then 15, there are no more lecture anymore. So that what we do, we have 2 slots here. we have tutorial. For this lecture. No, the whole lecture, 5 lecture here, the whole lecture. Yeah, but yeah, and 5 lecture. But we can go to the evening. Because there are no tutorial. Okay. And then in the station morning we have tutorial. And then in this, in your job, presentations, 5-minute talks, or the afternoon session here. Okay, that is we plan to do. After that, it is the same. Because maybe 17, we don't have tutorial card. We have to put other research talk on that session tomorrow. Okay, but I will tell you maybe day by day. Okay. We send the link in the Line open chat for you to give the topic and upload slide. For this talk, student talk, 5 minutes. That's here you can put some slide by adding by using that Google form. Okay. Any question you can ask me about in Line group also. Could be tomorrow, right? We have to arrange to get up in the presentations. Okay, that is a good question. Okay, I think in 15 morning we can arrange it so that yeah, just send in 14. Okay, all day. What is going to be for 14 talks? Okay, it's about black hole things. Research talk 1 hour. And maybe if I find someone to talk this slot, I will put it in. Okay. Or if you want to talk, it's okay. Okay. Now I think no more announcements. Yes. Can get it in to take the dinner box. Yeah. Okay. Go for dinner.